So in this topic we will be seeing the EDF scheduling of accepted sporadic jobs, where S1, S2, S3, S4 they are sporadic jobs. So if we take how the acceptance test is executed, we will take an example. So take S1. In this S1 we are having two parameters, 17 and 4.5, where 4.5 is the execution time of S1 and 17 is deadline. So we need to check for 17. So 17 is it is including the frames 1, 2, 3 and 4. And if we take the slack time of the frames 1, 2, 3 and 4 which are within the deadline 17, then the total slack time available it is only 4. Okay, he has given, we can't estimate it by the figure, but he has given it in the textbook that the total slack time till the frames 1 to 4 it is only 4. So what we'll do, we'll see that 4 is less than 4.5, the required execution time of S1. So what we'll do is we'll reject S1. So in that way will be the same kind of acceptance test. It will be implemented for S2, S3 and S4. Implementation of acceptance test. The acceptance test consists of the following two steps. The first one, the scheduler first determines whether the current total amount of slack in the frames before the deadline of job S is at least equal to the execution time E of S. If the answer is no, it rejects capital S. If the answer is yes, the second step is carried out. So what is the second step is, in the second step, the scheduler determines whether any sporadic job in the system will complete late if it accepts S. If the acceptance of S will not cause any sporadic job in the system to complete too late, it accepts S, otherwise it rejects S. So this is the equation which shows the slack time, calculation of estimation of slack time. If S is accepted, the amount of slack sigma before its deadline is equal to the above equation 5.6a. Suppose that the deadline D of the job S of D, E being tested is in frame L plus 1. The current total amount of slack time sigma C of T, L in frames T through L can be computed from the initial amount of slack time in these frames according to the below equation 5.6b. Optimality of the next topic, it is optimality of cyclic EDF algorithm. So what we can optimize here, it is we can optimize the way they are scheduled. Like we can verify whether the slack times they are correctly utilized or not, whether any sporadic job it is making the other thing wait. So like this thing we can optimize the cyclic EDF scheduling algorithm. The next topic, it is practical considerations and generalizations. Handling. So in this, the first topic, it is handling frame overruns. So whenever a frame overrun occurs, frame overrun means whenever any job in a frame it is executing more than the frame period, then what to do? There are two cases. One thing is to omit the execution, the other thing is to continue the execution. If nothing happens to the system, if the execution is continued even by frame overrun, then we have to continue the frame overrun. But mostly in many cases better not to avoid the frame overruns. Mode changes. Coming to mode changes, mode change occurs when the system is reconfigured, and mode change it too can be executed like a job as a aperiodic job or sporadic job. And when it is executed as an aperiodic job, at each point of execution of that aperiodic job, what we'll be doing is we'll be inserting the new schedule of the new mode into the system when the mode change is executed as an aperiodic job in the timeline. So gradually what we'll be doing is we'll be removing the older schedule of the previous mode and we'll be replacing it with a new schedule, and finally we see that the mode change is implemented. So due to a mode change, some of the aperiodic jobs or some of the periodic jobs, if they won't meet their deadline, they need to be deleted. And if the mode change, if it is implemented like a sporadic job, then we will be doing the same thing. But what we'll be doing is we'll be trying to implement a strict completion time, that we will be worrying much about the deadline and general workloads and multiprocessors. So what about this third topic, general workloads and multiprocessors? He has taken an example to explain this topic. So this is the example where there is a system bus which is used for data transfer between the CPUs and the I/O. So the system bus is connecting the CPUs and the I/O. So in order to calculate the workload of the CPUs or the scheduling of the CPUs, how they are scheduled, then what it says is it is enough to calculate the schedule of the system bus. So that is the thing present in this diagram, which this diagram gives the information to us, and this is the same thing it is implemented in the flight information system of the Boeing aeroplanes. So the next topic it is the algorithm for constructing static schedules. The algorithm which we will be using it is the iterative network flow algorithm, or in short the INF algorithm, where to construct the algorithm we will be using a network flow graph. And a network flow graph, it is the one shown in this diagram, in this slide. It is having a source vertex and a set of vertices referred to like jobs and a set of vertices referred to like frames, and there is one more vertex called sink. So source is the vertex at which indicates which jobs are getting executed at the 0th release time, and jobs, they indicate the jobs, what are the jobs, and the links between the jobs and frames, they indicate which jobs are executing in which frames, which jobs are executing, which jobs classes are getting executed in which frames. And finally the sink, it refers to the end limit of the hyper period, or the total amount of the hyper periods. So finally by that period all jobs, they will be completing their execution. This diagram, it is a network flow graph. It is also a network flow graph. The difference between the one in the previous slide and this slide is, the one in the previous slide, it is a generalized one, whereas this one, it shows an example scheduling in terms of a network flow graph. The maximum flow of a network flow graph defined above is at most equal to the sum of execution times of all the jobs to be scheduled in a major cycle. A major cycle, it is nothing but a hyper period. The set of flows of edges from job vertices to frame vertices that gives the maximum flow represents a feasible preemptive schedule of the jobs in the frames. Specifically, the flow of an edge ji, j from a job vertex ji to a frame vertex j gives the amount of time in frame j allocated to the job ji. And the next topic, it is post processing. What is